Let's talk about Chapter 6. In Chapter 6, we will cover exponential and logarithmic functions. Why do we want to talk about exponential and logarithmic functions? Well, first off, both have numerous applications within nature. Exponential functions often model population. Logarithmic functions are often used in sound waves. And exponential and logarithmic functions are each other's inverses. Before we begin with exponential functions, I just want you to take a little bit of time to review our exponential rules. We've seen these previously, but you should still make note of all of these as we will need to use many of them as we talk about our exponential functions. When talking about exponential functions, we will say in general an exponential function is a of t equals a times b raised to the t, where b is the base, a is an initial value, and t is any real number. T often represents time. If b is greater than 1, this is representing exponential growth. If b is between 0 and 1, this is representing exponential decay. Let's look at a couple examples. State whether the following represents exponential growth or decay and the initial value. In our first example, we have y equals 8 times the quantity 5/4, all raised to the x. Here we would say that this represents exponential growth. This represents exponential growth because our base b is 5/4, and 5/4 is greater than 1. The initial value would be 8. The initial value is 8 because the value of a is equal to 8. Another way to think about your initial value is to plug in 0 for your exponent. So our exponent x, set that equal to 0. This would simplify to 8. So that gives you another way to find your initial value. Looking at our second example, y equals 2 times 2/9 raised to the x, we would say that this is exponential decay. This is exponential decay because 2/9 is less than 1. The initial value here would be 2. The initial value is 2 because the value for a is 2. Also, when plugging in 0 for x, we would get that this equation equals 2. Let's look at one more example. The equation y equals 5x. As we look at this, 5 is what is being raised to the power of x, so 5 is our base, 5 is greater than 1, so this is exponential growth. What's our initial value? We don't see any value for a sitting here, but remember that anything can have times 1 put in there and it's still the same. So we would say that the initial value is 1 when we're thinking about it with what is our value for a. If we think about it the other way, by saying let x equal 0, what does y equal? It's a little bit easier to see that our initial value should be 1. 5 to the 0 is 1 because anything raised to the power of 0 is 1. So if we plugged in 0 for x, we would get that y equals 1. Thus, our initial value is 1. We want to talk about exponential growth or decay, where we have a certain rate at which we are growing or decaying. We notice that our formula a of t looks slightly differently here. A of t is now equal to a times b raised to the r times t. R is simply our growth or decay rate. We will use this formula in a few examples in just a little bit. We also want to talk about interest while we're here, though. Interest is often modeled with an exponential function. The interest formula is a equals p times the quantity 1 plus r over n, all raised to the n times t. A is the account value, P is your starting principal, R is the interest rate, N is the number of times compounded, and T is the time measured in years. Keep in mind that N is the number of times compounded specifically in 1 year. When we're looking at finding N for our interest formula, this table might help you. So if we're saying we're compounding annually, N would be 1. Semi-annually, N would be 2. Quarterly, N would be 4. Monthly, N would be 12. Daily, N would be 365. Hourly, N would be 8,760. But what if I said we were compounding continuously? Well, we could keep in mind some upper level math. There's a letter E. It is the natural number E. It's found on your calculator. And it's approximately equal to 1 plus 1 over n raised to the n as n increases without bound. The letter E will be used for continuous compounding. The letter E is the number found on your calculator, and it's actually used to model many real-world exponential models. So on this idea of continuous, we can talk about continuous growth or decay, or continuously compounded interest. So these are two other formulas that we will find handy as we start to look at a few examples. For continuous growth or decay, we have the formula A of t equals A times E raised to the RT. If we're talking about continuously compounded interest, we use A of t equals P times E raised to the RT. Let's look at our first example. The number of bacteria in a culture is given by the function n of t equals 900 times e raised to the 0.5 t, where t is measured in hours. What is the relative growth rate of the bacterium population? Well, the growth rate is the value of r. So it's what we have up in our exponent that we're multiplying with t. So our relative growth rate would be 0.5. What about the initial population of this culture? Well, our initial population is that coefficient on E. It's that value for A that's out front. So that would be 900. Okay, here's a problem that gets us to do a little bit of math. How many bacteria will be in the culture after 5 hours? Well, T represents hours, so let's let T equal 5 and plug it in. You'll need to use your calculator for this, and please do try so that you can make sure you're coming up with the same answer. Rounding to the nearest whole number, we get 10,964. Moving to our next example. The population of the world in 1987 was 5 billion, and the annual growth rate was estimated at 2% per year. Assuming the world population follows an exponential growth model, find the projected world population in 1989. To make this problem a little bit easier on us, we're going to work in billions. So we'll just use 5 for our initial value, and we know that our answer that we get will need to tack billion onto the end of. So our initial population we would say is 5. Our growth rate is 2%. 2% as a decimal is 0.02. So we're going to plug that into our population growth model, knowing that this is a continuous growth. So P of t will equal 5 times e raised to the 0.02 t. Now to find the projected world population in 1989. Well, 1989 is 2 years after 1987. So we'll use the value of 2 for t. Plugging in 2 for t, we get 5.2. Now, as we said before, our answer is in billions, so our projected world population in 1989 was 5.2 billion. Certain radioactive material decays in such a way that the mass remaining after t hours is given by the function m of t equals 360 e raised to the negative 0.025 t, where m of t is measured in grams. We want to do two things. First, find our initial mass, and second, find how much remains after 45 years. Well, the initial mass is our initial value, so we can see from just looking at our function, the initial mass is 360. To find how much remains after 45 years, we will plug in 45 for t, because t is given in years. So m of 45 is equal to 360e raised to the negative 0.025 times 45. Punching that all into your calculator, you should get 116.87. So that's how many grams will remain after 45 years. If $8,000 is invested in a bank account at an interest rate of 9% per year, find the following. First, the amount after 13 years if interest is compounded annually. Then we will look at quarterly, then monthly, and then we'll look at continuously. To do the first three parts, we need the interest formula that states A equals P times the quantity 1 plus R over N raised to the N times T. Plugging everything in for our first part, if we're compounding annually, we're compounding once per year. So N would be equal to 1. Our rate is 9%, so our value for R is 0.09. Our initial value, the initial principal in our account, is $8,000, and we're leaving it in there for 13 years. So plugging everything in and entering it into our calculator, we should get, rounding to 2 decimal places since we are dealing with money, $24,526.44. Now, as we do the next two parts, the only thing that needs to change is our value for N. We see N in 2 different places. N is in the denominator, and it shows up in the exponent. So we change our value for N, simplify using our calculator if needed, and we get $25,443.83. Finally, compounding monthly, our value for N would be 12, so making the appropriate changes. Entering it all into our calculator, we should get $25,663.66. Now, when we talk about compounding continuously for our next part, we need our different formula. We need the formula A equals P times E raised to the RT. Our principal is still 8,000, our rate is still 0.09, and our time frame is still 13 years. Plugging this into our calculator, we should get $25,775.94. I want you to be able to think about the graphs of exponential functions. I will not require you to graph an exponential function, but I will require you to look at the graph of an exponential function and state what the function is. We will cover a few examples of stating what an exponential function is by looking at its graph, but to get us started with that, we need to first just see the graphs of some exponential functions. In general, this is what our exponential function will look like when graphed. Notice there are two different versions of our graph, one for where b is greater than 1, and one for where b is between 0 and 1. A few things to note with this. These are one-to-one functions, which means that they will have inverses. There is a horizontal asymptote at y equals 0. This will hold true as long as our graph is not shifted using transformations. The domain is always going to be negative infinity to positive infinity, and our range, again, as long as it's not shifted, will be from 0 to infinity. There is no x-intercept. The y-intercept is 0, 1. Again, this is as long as there is no shifting taking place. When our value for b is greater than 1, our graph is increasing, and when our value for b is between 0 and 1, our graph is decreasing. Now, again, I'm not going to have you graph an exponential function, but if you were to want to graph an exponential function, these are your steps. So given an exponential function of the form f of x equals b to the x, graph the function by first drawing the horizontal asymptote. Second, plotting your y-intercept, 0, 1. Then you'd plot your key point. Your key point, we can see on the previous slide, is the point 1b. We notice it occurs on both our increasing and our decreasing graphs. So after we plot our key point, then you're going to draw a smooth curve so that it looks similar to one of our two versions of our graph, whether it's increasing or decreasing based on our value for b. Now, of course, graph transformations can and often will happen, so we want to be aware of what transformations could take place. So graphs can be transformed using the same techniques we've discussed previously on other functions. So we could have horizontal shifts, vertical shifts, we could have vertical or horizontal stretching or compressing, and we could have reflections about the x or the y-axis. These are going to be important to keep in mind, especially as we're looking at a graphed function and trying to state the equation of that exponential function. So, when determining a function from a graph, these are our three basic steps that we will follow. First, we want to define the horizontal asymptote. This will tell you about your vertical shift. It's nice to find that vertical shift first. The second thing that you're going to do is you're going to find a couple nice points. And we'll see what I mean by nice points when we get to our examples. Our third thing that we're going to do is we will use the nice points to solve for the base and then any stretching factor that we may have going on. So let's get to an example. The following function has the form f of x equals a times b to the x plus k. State the function. And we see a graph. First, we want to try to find our horizontal asymptote. As we look at this, the horizontal asymptote appears to be down here at y equals negative 4. So we'd say the horizontal asymptote is y equals negative 4. What this tells us is our vertical asymptote has been shifted down 4 units from where it was on our basic function. So that means our function that we're dealing with has been shifted down 4 units. This tells us about our value for k. Now, let's find some nice points. There's 3 nice points that we can see quickly looking at our graph. Maybe even more if we looked a little bit further. But the first nice point that we see is -2, 0, and another one is 0, -3. Now we could also have used -1, -2, but I like to use points that have a 0 in there because it's nice trying to plug in zeros. So what we're going to do is we're going to take these two nice points and we are going to use them as we try to state our function. So far what we know is that our graph has been shifted down 4 units. That means our value for k is -4. So we would have f of x equals a times b to the x minus 4. So let's try to plug in our second nice point. Let's plug in the point 0, -3. We're plugging in 0 for x, and we're saying that should equal -3. So we would have -3 equals a times b raised to the 0 minus 4. B raised to the 0, remembering our exponential rules, would be 1. So that means we have -3 equals a minus 4. Now we should be able to solve for a by adding 4 to both sides. So we would get that a equals 1. So now we're going to plug what we know for a into our function, and we're going to use our other nice point, -2, 0. So when we plug in -2 for x, we should have it equaling 0. So 0 equals 1 times b to the -2 minus 4. We know that a equals 1, so we've plugged that in. We know that k equals -4, so we've plugged that in. And we're using the point, an x value of -2, a y value of 0. Now, as we begin to simplify this, 1 times anything is just that, something. And so we have 0 equals b to the -2 minus 4. Well, let's add 4 to both sides, trying to isolate our variable b. So we have 4 equals b to the -2. Well, let's think about our exponent rules and how could we look at this slightly differently. We could say that 4 equals 1 over b squared. Now this is going to be helpful as we start to try to solve for b. Multiply both sides by b squared, divide both sides by 4, and then take the square root, and you would have b equals 1 over 2. Again, our steps there was multiplying both sides by b squared, then dividing both sides by 4. So you'd have b squared equals 1 over 4. Then take the square root of both sides, giving you b equals 1 over 2. Now we know the value for b, the value for a, and the value for k. So we can state that the function that's been graphed is f of x equals the quantity 1 over 2 raised to the x minus 4. Again, we want to state the function that has the following form, f of x equals a times b raised to the x plus k. And we have our function graphed for us here. Again, the first thing we're always going to do, find your horizontal asymptote. Looking at this, we would say that the horizontal asymptote is y equals 7. This tells us that we have a vertical shift up of 7. Next, we're looking for our nice points. Where are the nice looking points? Well, 2 nice points that I'm going to use here for this example is -1, 3 and 0, 5. Now, it's always nice to plug in 0 for x first. So using our y-intercept first is going to be to our advantage. The reason that we want to plug this in first is because anything raised to the 0 is 1. Thus, we will be getting rid of b, having less in our equation that we're trying to solve for. Each time when we start a problem like this, we have 3 variables we're solving for, a, b, and k. Now k we find when we find our horizontal asymptote. So we already know for this problem that k is a positive 7. If we plug in 0 for x, we're getting rid of b in our equation, and we'll only have a left, so we'll be able to solve for it. So that's why we always want to use our y-intercept first. So, plugging in our y-intercept, 0, 5. If we plug in 0 for x, we know our equation should equal 5. So we have 5 equals a times b raised to the 0 plus 7, which really means that we have 5 equaling a plus 7, so a should equal negative 2. Now, we have our value for a, we have our value for k, so let's use our other point to find the value for b. Our other point is an x value of negative 1, y value of positive 3. So we should have 3 equals negative 2, which was our value for a, times b raised to the negative 1 plus 7. 7 was our value for k. Well, let's start this out by subtracting 7 from each side. We will have negative 4 equals negative 2 times b raised to the negative 1. Divide both sides by negative 2, trying to isolate b. We get that 2 equals b to the negative 1. Well, again, using our exponent rules, this would mean that 2 equals 1 over b. So solving for b, we would have that b equals 1 over 2. To do this solving, you're going to take both sides times b. So you'd have 2b equals 1, divide both sides by 2, and you'd have b equals 1 over 2. So this means our function is f of x equals negative 2 times the quantity 1 over 2 raised to the x plus 7. Now it's time to shift gears. We're going to start talking about logarithmic functions. Logarithmic functions are the inverses to exponential functions. A logarithmic function is of the form y equals log base b of x, where b is the base, b has to be greater than 0, and b cannot equal 1. There's a relationship between logarithmics and exponentials. A log base b of x equals y is the same as b to the y equals x. We will use this relationship as we are trying to evaluate our logarithms. When evaluating our logarithms, we're trying to solve a logarithm of the form y equals log base b of x. We want to ask ourselves to what exponent must b be raised in order to get x. This sometimes is a little bit easier to think about because we've dealt with exponents a lot more in our mathematical careers. So when rewriting into exponential form, it's a little bit easier to see. And we will practice this with some examples in just a bit. But first we need to talk about the common logarithm and the natural logarithm. The common logarithm is a logarithm with the base of 10. It's often written without a base, so you'd see log of x equals y. This is the log that is found in your calculator, spelled out log or log x. The natural logarithm is the logarithm with the base e. It's written as ln of x equals y. So in your calculator, you would either see ln or you'd see ln x. These are the two logarithmic functions that are found in your calculator. And for most of you, these are the only two logarithms that are found on your calculator. So if you're wanting to use a calculator to find logarithms, you'd have to use a change of base formula. So the change of base formula allows us to work with logs that are not base 10 or base e. So if we have log base b of x, we could type into our calculator log x divided by log b, or we could type into our calculator natural log x divided by natural log b. make sure that you're either using log both times or using natural log both times. As we start to think about our logarithms, we're going to think about our graphs of logarithms as well. And if you look at these logarithmic graphs on their side, give them like a 90-degree turn, you're going to see that they look a lot like our exponential graphs. And that's because of the relationship between exponential and logarithmic functions, they're inverses. And so there's going to be this relationship that we see, this similarity that we see between them. So let's go ahead and take a look at what we have for our graphs here. And again, keep in mind, I won't have you graph these, but I will have you look at a graph and state the function. So for any real number x, the constant b greater than 0, b not equal to 1, we can see the following characteristics of the graph f of x equals log base b of x. So they're a one-to-one function, meaning they have an inverse, and that inverse is going to be an exponential function. We have a vertical asymptote of x equals 0, domain of 0 to infinity, a range of negative infinity to positive infinity. We have an x-intercept at 1, 0. There is a key point at b, 1. There's no y-intercept. It's increasing if b is greater than 1, and it's decreasing if b is between 0 and 1. And of course, all of these hold true unless we've had shifting going on. If we have any graph transformations going on, we might have a y-intercept or we might have a different x-intercept. So if I were to ask to graph a logarithm, which I won't have you do, but you might do later on in your life, given a logarithmic function of the form f of x equals log base b of x, you would graph the function by first drawing and labeling your vertical asymptote. Then you would plot your x-intercept, plot your key point, and then you'd draw a smooth curve, keeping in mind the domain, the range, the vertical asymptote, making it look like one of those two versions of the function that we just saw, based on whether b is greater than 1 or between 0 and 1. Now, as I said, graph transformations can and will happen. So the different transformations that we know, the horizontal shifts, vertical or horizontal stretching or compressing, and reflections about the x or y axis, all of those are transformations that may happen. So we need to keep those in mind as we're thinking about the graphs of these functions. Now, before we're ready to start thinking about our graphs and talking about the graph and finding the function from that, we need to talk about logarithmic rules. We know our exponential rules already, so we didn't have to take a break and talk about that when we were talking about finding our function based off of our graph, but we don't know these logarithmic rules. So we need to talk about them for a little bit, make sure we understand them, practice them a little bit, then we'll be able to go from being given a graph to stating the function. So, some logarithmic rules that you need to keep in mind. First off, there's the product rule. Log base b of m times n is equal to log base b of m plus log base b of n. M and n are positive real numbers. Next, we see our quotient rule. The quotient rule is log base b of m divided by n. This is equal to log base b of m minus log base b of n. Finally, the product rule, log base b of m raised to the k equals k times log base b of m. K can be any real number. Remember, m and n had to be positive real numbers. And then just a few other rules that are helpful with solving with our logarithmics. Log base b of b is equal to 1. Log base b of 1 is equal to 0. Log base b of b to the k is equal to k. And b raised to the log base b of k is equal to k. These last four especially will be useful to us as we are trying to find the equations of our graphed functions. Let's practice our rules. Looking at this example, we have log base z of b to the third raised to the second. Well, our exponential rule tells us that's log base z of b to the sixth. Then we can go back to our logarithm rules. And our logarithm rules, we could use the product rule and say this is 6 times log base z of b. If I gave you something like log base 6 of 6 plus log base 6 of y, we could say this is 1 plus log base 6 of y. Looking at our next example, we see log base 2 of 1 over 32. Let's think about 32. 32 can be written as 2 to the fifth. But it's not going to do us any good if it's in the denominator. So let's bring that up to the numerator and write it as 2 to the negative 5. So we have log base 2 of 2 to the negative 5 because 1 over 32 is the same as 2 to the negative 5. We're now thinking about our log rules. This is like our rule log base b of b to the k equaling k. So that means this should equal negative 5. Let's look at a longer problem. Let's look at 6 times log base 2 of 8 plus log base 2 of y minus log base 2 of 6. And let's work on condensing this down. We're going to look at our first piece and we're going to think about our power rule. So our power rule says we could rewrite that as log base 2 of 8 to the sixth. Then we could use our product rule and combine those first two logarithms together. Now when combining using our product rule and quotient rule, we're going to work from left to right unless there's parentheses. So since we don't have parentheses, we're going to combine our first two and then we'll deal with the next one. So combining the first two, let's also simplify 8 to the sixth. So we have log base 2 of 262,144 y minus log base 2 of 6. Now that subtraction in there tells us we are going to divide. So we'd have log base 2 of 262,144y divided by 6. We can simplify that fraction and have log base 2 of 131,072y divided by 3. Let's continue to look at a few more examples just to make sure that we're getting lots of good practice in. Log base 5 of b minus log base 5 of b plus 2. The subtraction there is telling us use your quotient rule. So we have log base 5 of b over b plus 2. Looking at our next example, log base 5 of the quantity y squared minus 4 plus log base 5 of the quantity y squared plus 2. That addition there is telling us to use our product rule. So we have log base 5 of y squared minus 4 times y squared plus 2. If you wanted to, you could FOIL and leave it at log base 5 of y to the 4th minus 2y squared minus 8. Now your homework should accept either this final simplified one or the previous line above. What if I gave you the natural log of e raised to the 6th? Well, the natural log is base e, so this would be like one of our rules, and we'd have just 6. What about e raised to the natural log of 2? Again, this is like one of our rules because the base for our natural log is e, so this would be 2. What if I gave you e to the natural log of the square root of 9? Well, again, this looks like one of our rules because the base for the natural log is e. So we'd have the square root of 9, but we know the square root of 9 is 3, so we would answer with 3. Now let's practice rewriting, going back and forth between the logarithmic and the exponential form. So if I had log base z of w equals a, we want to rewrite this into exponential form. The biggest thing to keep in mind is your base always stays the base. So since we have log base z, the base of our exponential will be z. The other two parts switch. So we would have z to the a equals w. Notice in the logarithmic form, w was on the same side of the equal sign as z is, and a was on the opposite side of the equal sign. Once we're in the exponential form, a and w switch. So a is now on the same side of the equal sign as z, and w is on the opposite side of the equal sign. The biggest thing to keep in mind is your base always stays the base. So what if I gave you an exponential and asked you to write it into a logarithmic form? For example, 4 raised to the t equals a. My base here is 4, so I know I have log base 4. And I'm going to have log base 4 of a equaling t. Keeping our rules in mind, let's start trying to solve for x. What if I gave you log base a of a to the negative 3, and I said that equals x? We need to solve for x. Well, always look at your logarithm and try to simplify your logarithm as much as possible. So we would have log base a of a to the negative 3, that simplifies to negative 3. So our left-hand side simplifies to 3, our right-hand side is just x, so we know negative 3 equals x. What about log base a of a to the y equals x? Again, simplifying using our logarithmic rules, we see that the right-hand side is still x. The left-hand side, using our log rules, is just y, so we have y equals x. And one more example, very similar. Use your log rules, and we get 8 equals x. We've had enough practice now that I think we are ready to try finding the function based on our graph. There's a few more steps to this. First, we want to look at which side of the vertical asymptote the function is on. When it's on the left side, there's been a reflection over the y-axis, so we're always going to look for that first. Then we're going to look for the vertical asymptote and ask ourselves, has it been moved? This tells us about the horizontal shift. Then we're going to look for the x-intercept 1, 0. If this point exists, then there is no vertical shift. If not, then look for the value of y at x equals 1. This tells you the vertical shift. Next, we look for the key point, B1. If there's no point B1, look for a nice point and make note of the Y value. This Y value is going to tell us our stretch. This also tells us about the reflection over the x-axis if it has a negative Y value. And finally, the last thing we do is we find B. We find B by plugging in the key point and using all values found for reflections, shifts, and stretches. Before we see our example, it's nice to just go ahead and look one more time at what our logarithmic graphs look like. Again, this is a slide that we've seen earlier, so we're not going to spend much time talking about it here. We're going to jump straight into our example. So, state the following function of the form f of x equals a times log base b of x plus c plus d. Notice that c is on the inside with the x. We're told that f of x passes through -1, 0 and 1, -2, and we're shown the graph. You're given our two nice points that we're going to use, and your homework should give you these nice points as well. The graph we see here is to the right of a vertical asymptote, so no reflection about the y-axis, so this is nice for us. Next, we're going to look for our vertical asymptote. We see our vertical asymptote here is graphed at x equals -2. This tells us that it's been shifted left by 2 units. Now, we're going to look at our x-intercept. Our x-intercept should always be 1 unit away from our vertical asymptote. Normally, our vertical asymptote is x equals 0, and our x-intercept would be at 1. So they're 1 unit apart. So we're going to make sure that our x-intercept stays 1 unit away from our vertical asymptote. As long as it's just 1 unit away, then there's been no vertical shift. So here our x-intercept being at -1, 0, it is just 1 unit away from our vertical asymptote, so we know that there's been no vertical shift. So far we have no reflection about the y-axis, we've shifted left by 2, and there is no vertical shift. So that allows us to fill in a little bit of information about our function. With there being no vertical shift, we know d equals 0. No reflection about the y-axis tells us that we know there's not a negative that we have to introduce somewhere. And knowing that it's been shifted left by 2 tells us our value for c. So I just want to highlight our 2 key points here. Our key points are our x-intercept and the point 1, -2. That key point 1, -2 tells us our stretch. We're being stretched by a factor of -2. Now a is always our stretching factor, so this would tell us that a equals -2. So we have a is -2. We have a shift left of 2 units. Now remember, with our shifts left and right, left would be a +2, right would be a -2. So our value for c would be a +2. And we know that we've not shifted up or down, which means that d is 0. So right now, as it stands, we have the function f of x equals -2 log base b of x plus 2. This is using all of the information that we have so far. Now we will do more examples where we can see what happens if we do have a reflection about the y-axis. And that is a case that you will want to pay attention to for your homework problems. Moving forward with this example, we're going to use that key point 1, -2. So we're going to plug in the value of 1 for x and set it equal to the y value of -2. So that means -2 equals -2 log base b of 1 plus 2. Well, we know 1 plus 2 is 3. And I dropped my negatives on both sides. So you could at this point still have -2 equals -2 log base b of 3. I chose to make both sides positive at this point by multiplying both sides by a -1. Your next step would be trying to get your log isolated. So that means we want to try to get rid of that coefficient of 2. So we divide both sides by 2. We'd have 1 equals log base b of 3. So now is when we have to start rewriting things, asking ourselves, what would b equal? Well, if we rewrite the logarithm as an exponential, it'd be base b raised to the first equals 3. So that means b equals 3. Well, now we know the last missing piece, so we know that our function f of x equals -2 log base 3 of x plus 2. Let's try one more example. Again, we're working with a function of the form a times log base b of x plus c plus d. Our function passes through 2, 0, and 0, 2. Now, as we're looking at this graph, the first thing that we look at is whether our function is on the left or the right side of our vertical asymptote. In this case, it's on the left side of our vertical asymptote. So the graph is on the left side of the vertical asymptote, so that tells us there's a reflection about the y-axis. Now, when thinking about reflections about the y-axis, that was when we put a negative in with the x. And so we're going to see in just a little bit, after we finish gathering all of our information, how we're going to use a negative to show the reflection about the y-axis. So for now, we're just making a note, there's a reflection about the y-axis. We've got to keep that in mind. Next, we're going to say, where's my vertical asymptote? My vertical asymptote is at x equals 3. So this tells me I've been shifted right by 3 units. Then we look for our x-intercept. Our x-intercept has to be just 1 away from where our vertical asymptote is. And it is still just 1 unit away from our vertical asymptote. This tells us there's been no vertical shift. And for all of your homework problems and the test problem, you will not see a vertical shift. Now, our key point is the point 0, 2. So this means our stretch factor is 2. So these are all the things that we want to gather before we start trying to plug things into our function. So we say, is there a reflection about the y-axis? Yes or no? Where's our vertical asymptote? Is our x-intercept just 1 away from our vertical asymptote? And then, where's our key point? The y value of our key point is going to be our vertical stretch. So now that we have all of these things, we're going to plug them into our function. So what we have, vertical stretch of 2, that means a is equal to 2. We don't know anything about our base b just yet. We know that we've shifted right by 3, so we have x minus 3. But then our reflection, we have to put that inside our function with x. We're going to make the x minus 3, that quantity, negative. Keep in mind our order of transformations that we learned back when we first talked about graph transformations. We do our left and right shifting before we do our reflections. So that's why you have negative, then parenthesis x minus 3, close your parentheses. And we're taking the logarithm of that whole quantity. Now, our key point is 0, 2. So we're going to use the key point of 0, 2, plug everything in, and we are going to find our value for b, our base. So we're plugging in an x value of 0. This should equal a y value of 2. So 2 equals 2 log base b of negative parenthesis, 0 minus 3, close parenthesis, close your last set of parentheses. Start to simplify. Well, 0 minus 3 is negative 3. We have that negative still in front, so negative 3 is a positive 3. So we have 2 equals 2 log base b of 3. Divide both sides by 2. 1 equals log base b of 3. Rewrite using exponentials. We get b equals 3. So now we plug our value for b into our function. And we have f of x equals 2 log base 3 of negative parenthesis x minus 3 close parentheses. We need to start talking about solving equations involving exponentials or logarithms. When we can find a common base, it's going to be a lot easier, but most of the time a common base is not going to be found. So we're going to start talking about solving when a common base cannot be found first, and then we'll see an example where, hey, if we have a common base, things get a little bit easier. So if we don't have a common base, we will take the logarithm of both sides using either our common log or natural log. And then we're going to continue to simplify using log rules as necessary. Now, please note that your answer will most likely be a logarithm. Make sure that it is simplified. Do not answer with decimals unless you are directed to do so. Now, we're able to follow these steps because of the one-to-one property of logarithms. If the natural log of x equals the natural log of y, then it has to be the case that x equals y. And if x equals y, then it has to be the case that the natural log of x equals the natural log of y. So this is what we're using when we are solving these problems. A few general rules for solving. If the equation contains an e, use the natural log so we can get rid of e. Make sure to do the same thing to both sides of the equation. That's always important. And then an extra step that you always want to make sure to do is check for an extraneous answer. So you always want to look and make sure that your answer works out. Sometimes you will break no math rules all throughout your problem. You'll come up with a couple answers and one of them is not a solution. So you always want to make sure that you check your solutions. When you're working your problem, always simplify each side of the logs or exponentials to just one term per side before moving forward with solving. You always want to have both sides simplified before you start throwing logs in there or exponentials in there in order to solve your equation. Let's look at an example. Our first example here, we have 7e to the x minus 11 equals 13. So the first thing we want to do is we want to try to move things around so we only have one term on each side. And ideally, we'll have just our exponential or just a logarithm on each side before we start to use all of our special tricks and rules that we know from our logarithms and exponentials. So this one, we're going to start by adding 11 to both sides. So we have 7e to the x equals 24. Now it'd be great if we could get e to the x by itself. So let's divide both sides by 7, even though we'll be left with a fraction. So e to the x equals 24 over 7. Now, we know that the natural log will cancel with the e. So if I took the natural log of both sides, my left-hand side would just be x. So let's do that. Take the natural log of both sides, and we're left with x equals the natural log of 24 over 7. Now, unless your homework asks you to answer with decimals, please leave it in this form. You might want to make sure that you put parentheses around the 24 over 7 as you're entering it into the computer. Let's look at another example. This one does not have e in there. As we're looking at it, we see that there's just one term on each side. There's nothing we can really do until we introduce some logarithms. So we're going to take log of both sides. And you can do common log or natural log. I tend to use natural log quite often. So I'm going to take the natural log of both sides. Now, the reason that I'm going to take a log on each side is that allows me to pull the exponent down in front. So my variable is no longer going to be stuck in the exponent, which is going to be nice. So using that power rule on both sides of my equal sign, I have x plus 2 times the natural log of 5 equaling x times the natural log of 4. Now let's distribute on that left-hand side. So we have x times the natural log of 5 plus 2 natural log 5 equals x times natural log 4. Now let's get anything that has an x all moved together on one side of our equal sign. So we'd subtract x natural log 4 from both sides, and then let's move that other term to the other side. So let's subtract 2 natural log 5 from each side as well. So now we have x natural log 5 minus x natural log 4 equaling negative 2 natural log 5. Well, now both terms on our left-hand side have an x in them. So we could factor that out. When we factor that out, we have x times the quantity natural log 5 minus natural log 4 equaling negative 2 natural log 5. Well, now to solve for x, we just divide both sides by what it's being multiplied by. So we divide both sides by natural log 5 minus natural log 4, and we'd find that x equals negative 2 natural log 5 over the quantity natural log 5 minus natural log 4. Now, our answer doesn't necessarily look pretty, but this is how we would leave our answer. What if we had 2 to the x equals 17? Well, again, we don't have anything that we can do to simplify either side before trying to introduce some logarithms to get our x out of the exponent. So let's just start by taking the natural log of both sides. So we have natural log of each side. That's going to allow us to pull that x down in front. So we have x times the natural log of 2 equaling the natural log of 17. Solve for x by dividing both sides by natural log of 2. So we have x equals natural log 17 divided by the natural log of 2. Notice that there's a natural log in both the numerator and denominator. This is not the same as natural log of 17 over 2. So please make note that this is natural log 17 over the natural log of 2. Let's look at our next example. Our next example has 8 raised to the 7x minus 10 equaling 2 raised to the 4x minus 10. Now let's look at our bases for just a second here. 8 is a power of 2, isn't it? 8 is the same thing as 2 to the third. Well, that means that we could rewrite this so that we have the same base on each side. Now, if you didn't notice that, you could continue to use our log rules and solve that way. But if we recognize that 8 is simply 2 to the third, we could rewrite this. So our left-hand side becomes 2 raised to the 3 raised to the 7x minus 10. Well, our exponent rules tell us that we have an exponent raised to an exponent. We're going to multiply those together. So that's really 2 raised to the 21x minus 30. Our right-hand side we've left the same all along. We've just been carrying it down. Something that's nice about when you get your base to be the same on each side is that now you can ignore your bases. You can look at just the exponents. If your bases are the same, then your exponents have to be the same too. So that means we could simplify this to just saying 21x minus 30 equals 4x minus 10. This is a much easier problem for us to solve. We don't have to worry about exponentials or logarithms at this point. We're just solving a nice equation that has only one variable in it. So now we'd move constants to one side, move variables to the other side. So subtract 4x from each side, add 30 to both sides. We have 17x equals 20. Solving for x, we divide both sides by 17. And we have x equals 20 over 17. Let's look at our next example. In our next example, we see e raised to the 6x equals 18. Right away, we see we can't simplify either side at all. So let's go ahead and take logs. We're going to use the natural log here because we have an e. So the natural log of e raised to the 6x equals natural log of 18. That's just 6x equals the natural log of 18. So divide both sides by 6, and we have x equals the natural log of 18, all divided by 6. Now again, be careful here. We're not saying 18 divided by 6, we're saying natural log of 18 divided by 6. So make sure that you are careful about how you're defining your numerator and denominator as you're entering your answers. So far we've been starting with exponentials and we're trying to solve them, and we've been using logarithms. What if we were to start with a logarithm and we were trying to solve it? Well, we're going to use exponentials. And when we're solving logarithms and using exponentials, this is when we're going to have to check our answers a little bit more carefully. So for this example here, we have natural log of the quantity 5x plus 3 equaling 2. Now there's just one term on each side of the equal sign. Since we have a natural log, let's use e, since that'll get rid of our log there. So our left-hand side will become 5x plus 3, and our right-hand side will become e squared. Now, e squared is just a number, so we can leave it hanging out like that. We are going to try to solve for x now. So solving for x, we'd want to subtract 3 from both sides. So we have 5x equals e squared minus 3. And then solving for x, we just need to divide by 5. So x equals e squared minus 3, all divided by 5. Now, to make sure that this works in your equation, you would want to go ahead and plug that back in and make sure that you are taking the log of a positive number. Remember, our log needs to be taking the log of a positive number. That has to be a positive number. Let's look at the next example. This next example looks a little bit different. We have log of x to the 6th equaling log x squared. This one looks a little bit different to us because our entire logarithm is being squared, not just what we're taking the logarithm of. So as we start this one, let's move both terms to the same side, setting it equal to 0. So we have 0 equals log x, quantity squared, minus log of x to the 6th. Now, we can use our power rule on that second piece there. So we have log x, quantity squared, minus 6 log x. Well, we can factor log x out of that, right? So that would mean that we would have 0 equals log x times log x minus 6. Now, we're kind of solving this like we did with our quadratics when we were first starting to talk about solving quadratics by factoring. We can now set each factor equal to 0. So we have 0 equals log x. Remember, when we don't have a base written, this is base 10. So this is really 10 to the 0 equals 10 to the log x, which means that 1 equals x. And looking at our other side, we would have 0 equals log x minus 6. So that means 6 equals log x, using our same trick with 10, we would see that 10 to the 6th equals x. And you could plug both of these in and they both will work. Our next example, we see 9 over 2 times log base 4 of x equals 4. We always start by trying to get our logarithm by itself. So let's multiply both sides by 2 over 9. Multiplying by 2 over 9 will cancel with that 9 over 2. So that means we have log base 4 of x equaling 8 over 9. Now, since we have log base 4, we're going to have base 4 introducing exponentials. So 4 raised to the log base 4 of x equals 4 to the 8 over 9. Well, now our left-hand side simplifies pretty quickly using our log rules, and we have x equals 4 to the 8 over 9. And you can plug that in and see that that will work as you're plugging it back in. This next example, we have quite a few logs running around, but notice all of them are base 3. Since they're all base 3, we're not going to be too worried about them as we start to simplify. The first thing that we want to do is we want to go ahead and use our log rules to combine these into just one logarithm on each side. So first, using our product rule, we would see that this is log base 3 of x times x plus 4 equaling log base 3 of 5. Now that we have just one log on each side, we can use our exponent rules to help us out. 3 to the log base 3 on each side, those cancel, and we're left with x times x plus 4 equaling 5. Now this is really a quadratic. Go ahead and multiply and then move everything to the left-hand side, and you'll have x squared plus 4x minus 5 equaling 0. And then try to factor that. It factors pretty quickly. We have x plus 5 times x minus 1 equaling 0. Set each factor equal to 0, and we have x equals negative 5 and x equals 1. Now, when we go to plug things back in and do a quick check and make sure they work, trying to plug in x equals negative 5 does not work. Notice your first term of our original equation was log base 3 of x. Well, if we're plugging in negative 5, that would be log base 3 of negative 5. We cannot take the log of a negative number. So that means negative 5 is not actually a solution for us here. So we have to cross it out, and we're just using x equals 1 as our solution. Now that we've practiced with solving a little bit, we can go back to some story problems, and we can work with our story problems a little bit deeper. So, a bacterium culture initially contains 2,000 bacteria and doubles every half hour. The formula for the population is P of t equals 2,000 e raised to the kt for some constant k. You need to find k for the following. So first, let's find k, and then we'll find the population size after 40 minutes, and then after 6 hours. Now, I'm going to let t be time in hours. So if I'm talking about doubling every half hour, my population size is going to be twice as big when t equals 0.5. It was initially 2,000, so when t is 0.5, my population size should be 4,000. So that's how I'm going to get this equation here. Plugging in 0.5 for t, I know my equation should equal 4,000. My only variable here is k, so I'm going to solve for k. Divide both sides by 2,000. We have 2 equals e to the 0.5k. Take the natural log of both sides. We have natural log of 2 equals 0.5k, which means natural log of 2 divided by 0.5 equals k. So we're going to use that for k. We're not going to round it. We're going to actually type that into our calculator every time that we need to use k. That way we have an exact answer. And we're going to answer our next two parts. So it asks about the population size after 40 minutes. Now remember, we said t was in hours, so 40 minutes would be 40 over 60 hours, or 2/3 of an hour. If you wanted to simplify that, you could. So p of 40 over 60, plugging everything in, we're going to get rounding to the nearest whole number. About 5,040 bacteria will be in our population after 40 minutes. Now, if we wanted to say what's the population size after 6 hours, we would plug 6 in for t. Crunch some numbers on your calculator. Again, round to your nearest whole number. And you will get 8,192,000 for your population size after 6 hours. Just a couple more examples left, and then we've wrapped up the chapter. The half-life of radium-226 is 1,590 years. If a sample contains 100 milligrams, how many milligrams will remain after 2,000 years? Well, we know that our population is going to follow this P of t equals some initial population times e raised to the kt. A half-life means that our population is down to half its size in a certain number of years. So if our initial population was 1, after our 1,590 years, our population size would be 0.5. So we're going to say 0.5 equals e raised to the 1,590 k, and we will solve for k. We get k equals the natural log of 0.5 divided by 1,590. Then we can plug in 2,000 to find out how much remains after 2,000 years. This is assuming that our sample started with 100 milligrams. So P of 2,000 equals 100 times E raised to our value for K times 2,000 is T. So we find out that there's approximately 42 milligrams left after 2,000 years. Alrighty, last example, the half-life of palladium 100 is 4 days. After 24 days, our sample has been reduced to a mass of 5 milligrams. What is the initial mass of the sample? Well, again, remember that our population size will be modeled by P of t equals initial population times E raised to the kt. Knowing our half-life, we could say 0.5 equals E raised to the 4k, because 4 is the amount of days for our half-life. Solving for k, we have k equals the natural log of 0.5 divided by 4. Now, we know that after 24 days, so t equals 24, our population size, our mass, is going to be 5 milligrams. So we could say 5 equals some initial population times E raised to our value for K times 24. Now we're solving for that initial population. And we get that our initial population is 320. That is all for Chapter 6. If you have any questions, make sure that you send them to me and let me know if you have any issues as you're working on your homework.